Hey guys, in the previous video I showed you how the standard vector, that is std vector library, is implemented, that is in C++. We implemented that right in from scratch in C. Now in this video we will be going to cover linked list. So we'll be covering single linked list and we'll see how it is different from a vector or an array, and also why it is needed. By the end of this video you will very much have a good idea as to why different type of data structures exist, right? So let's get started. You can see this was my vector. This was the last video. I'll create another called singly linked list dot c. Okay, so let's go here. So what is a singly linked list? Firstly, what is a linked list? A linked list is basically multiple nodes marked together using links which are having data. Okay, for example, we have an array. Let's say we have an array something like 1 2 3 1 2 3 4 and 5. So all the elements in this array, they are in a contiguous fashion, right? So this is 1, then this is 2, this is 3, this is 4, this is 5. Like, I'm not talking about the elements in themselves but the memory layout. So just for an example, if this array was of type int, and let's just say int maps to 4 bytes in this compiler, in that case, if at the starting position, at the 0th index, if the memory layout was something like 1000, then at the first index the memory layout would be 1004, because this is the initial memory layout and 4 bytes after that is the next element, right? So that's the idea of that. Now just one quick thing, if you go to vector over here and if you see this function that we created, where we were basically inserting after a given index, right? In the worst case this was taking us O of n time, right? In the worst case this was taking of O of n time, because maybe I would just have to, when I insert a value, let's say I want to insert at the front, then I would have to shift all of the values to the right by one position. So that was something bad, right? Similarly, if we wanted to erase something, in that case we would have to remove that node, we would have to remove that element in itself from the vector, and then we would have to shrink it, we would have to shift all of the elements to the left by one. So these were the main challenges in that. Now singly linked list is something which aims to solve this, right? So the idea is, in singly linked list we have nodes that are connected with each other. So we have nodes that are connected with each other, and each node is going to carry a value. Till now it's just like an array, okay, so these are all the indices. You can think of nodes as indices and they're all connected, right? In array also, we know after the 0th index we have first index, then the second index, and so on and so forth, and in each of these indexes we have values. So each node is going to carry a value. The only thing is, it is not in a contiguous fashion, it is not in a contiguous memory. So means the first node, let's say this is my starting node, after this the next node that I have, it need not be at the just next memory address offset by the size of the data type that it is holding, right? So what I'm saying is, if my first node is at something is at memory address, say something like 1000, and having a value 1, my second node can be at a memory address something like 2002, having a value 2. It can be anything, right? It depends on how the memory allocation is done and whatever block we are trying to get the memory for. But it for sure, there is no constraint for it to be in a contiguous fashion. Okay, So now we have seen that each node is going to carry a value. That's fine. But then how do we know from one node we have to, like, let's say this is the first element in my linked list, then from this I would want to go to the next one. How would I know that? For that we use a pointer. So sequential nodes are marked by pointers. Mainly, like, we use this keyword called next pointer. So next pointer, right? So now the thing is, if I convert this entire array that was here 1 2 3 4 5 to a linked list, it would look something like 1 would be pointing to 2, which would point to 3, let's say 4, and let's say 5, and let's just keep 5 at its place right now. Okay, so this is the first node, right? This can have a memory address something like 1000, and then the next node can have a memory address something like 2002, and then, like, the next node can again have a memory address something like 2016. The fourth node can have a memory address something like 1996, and the fifth node can have something like 1200. It can be anything, right? It need not be like in a contiguous fashion or something like that. So why are memory addresses important? Because the thing is, in an array, when we apply the subscript in an array, that is, in an array, when you apply this thing, so after this, when you go from here to I plus 1, this essentially means, like, in that contiguous memory block, which for an array it is like arranged in a contiguous fashion, just move to the next block. And by how many bytes you should move? By the size of the data type, right? By the size of the data type that you had. So if you see over here, in vector, so you see, like, this was the data, like this was the array that we are creating, and we were giving, like, we were allocating the capacity multiplied with the size of the data type, and then, like, whenever we would insert or whenever we would do something like that, we would then just move. So this was that I plus 1. But how would it know where the value is in I plus 1? That is because of the type of data that we have, and it's just that it is in a sequential fashion. So after the next index, I am going to go to the next element that I am holding. But for a linked list, it's not the case. For a linked list, we can have this like in any fashion. So enough of the talking, we will now just go to the code. So what are the things that we require? We require a value, we require a next pointer, right? So I'll be creating a linked list. Firstly, let me just include this stdioh library, and I'll be creating an entry point in our function, something like return 0, and that's it. So over here we are going to have our node. So this node is going to define like my linked list. Okay, so in this node I'm going to have two things. For this I'm also going to keep this as integer, but we can have generic data type as well. So int value, so this will be the value of the node, right? And the next will be the pointer where it points to, so that will be again struct node next. Okay, and then this will be node. So you can see like this is required because we are defining the struct over here, and if I just give it like node and something, it doesn't know what is node, so I would have to write it struct node. Okay, and also this is a self-referential data structure, so it references itself. So this is why we are using this next pointer, so that it can basically just point to the next node in that chain of linked list. So this will be node struct. Cool. Anything else that we require? So what are the things we would be requiring in a linked list? We would want to create a node, right? So if we want to create a node, we will be like getting a value, like we would be pushing a value, and then we would be getting a value in the sense we will be getting the node back itself. So let's have a function called create node. In that I will just pass a value, and this needs to return the node. And over here I'll just create a new node, something like that, and Yeah, so this is the node. What do we have to do next? So we would have to allocate something. We would have to allocate memory for this. So the memory is going to be of the size of node. Okay, I'll include this. So std lib.h, and yeah, so this is like I'm creating a new node, and for that node like this is the like size of the metadata that the node is going to be holding. So just like the previous video, we allocate some memory for this, and now for this new node, for its value we will be making it value, and by default let's just make the next as null. So this is a very crucial thing over here. So the next pointer to the, let's say, last node of that linked list, where basically the linked list ends, is going to be null. So for example, over here we had this linked list, right? 1 2 3 4 5. After this would be something like null, because this basically signifies, okay, this is where my linked list is like ends. Okay, cool. And we should just return new node. Cool. So we created a node. Now let's do a few more things. What are the other things that we can do? We can, like, okay, so now linked list has two more concepts. So there is a concept called head. Head is basically the starting point of the linked list. Okay, and we have tail. Tail is the end of the linked list. These are all concepts that we use for single linked list. Okay, so let's have a function called insert at head. Okay, and over here I'm going to get the head, and I'm going to get the value that we are going to do. And now what this insert at head is going to do is, basically this is going to modify the head. For example, I had something like 1 2 and 3. Now let's say I want to do something like insert at head, and like this was my head, and like this was basically my head, and this was having this node, and then this was pointing to this entire chain of nodes. And insert at head, let's say head, and then I would give something like 4. Then I would want my data to be something like this: 4 1 2 and 3, right? And after this, of course, there is null. So yeah, so this is essentially the function that we are trying to do. So as you can see, this head, this is just a node, right? And what I want to do is, I want to make a new head, I want to give it some value, and for that new head, the next element is going to be the current head, right? This means I would have to return the head as well. So this means the return type of this is going to be this. Okay, so firstly let's make a new like head. So new head, this is going to be this create node. So I'm just going to pass it this value. Okay, and now for this insert head, like I just created a new node, and this is having this value, and this is like having a null pointer to the next element. What I want is, for the new head, I want the next to be head. That's it. And I just want to return new head, right? Now let's say my head is null. In case my head is null, then it's fine, like nothing changes. I just create a new node, and the next pointer of that new node is going to be null, and I just return that, right? So yeah, that is that. What other functionalities do you want to have? Let's say, okay, so here's a fun thing. I want to insert, let's say I want to insert after a node. I want to insert after node. I want to have something like this, where basically after a given node, this is very rare because in linked list you don't normally track nodes like that. But yeah, let's say we are given a node. After that node I want to insert a new value, so I'll just show you how this is done. So let's say insert after node. So over here I'll be given a node and I will be given a value, and then basically what I want to do is after this node I want to put that value, right? And I don't want to do anything as such, right? Like I don't want to modify anything, or I don't want to return anything. I'll just, like, it will just be void. It's not just not going to do anything. But there can be cases when the current node is null. In that case I need to create that node itself. So I think it would be better if we just return something like this, and we just do a check that if the node is equals null, then we will be creating a new node using this, and we'll be giving this value, and we'll be returning the new node. If else, like if that is not the case, if this is not null, then nothing else, like we can just have this code outside, and if the node is null then we return this. If the node is not null, then for the next value of the node we will be having this as new node. That is, the element just after that node is going to be this, and we will be returning our node. But is that it? No. Why? Let's see. So this is very similar to that function that we did where we were inserting after a given index. Let's say I have something like 1, 2, 3 and 4 and null. Now let's say I want to insert after 2. So after the node 2, let's say I have the memory address of node 2. After the node 2 I want to insert the value 5. So I want this to convert into something like this, 3 and 4 and then null. So this means I just can't do this. Like I would have to also keep track, like I would also need the remaining elements, right? I would also require all the elements that were linked in the same chain. So what I'm going to do is we will be getting that. So in a temporary variable we will be storing whatever is the next element. So we are at this element 2, then for this element, like we are having this entire chain, right? So we will get this node and we'll store it somewhere. Then for the current node we will be marking the next as new node, and then for our new node we will be marking its next as temp, and that's it. And then we can just return the same node and like it's fine. So this was the insert after node. You can see this operation took us just O of 1 time. So the time complexity of this was O of 1 compared to something like a vector. Over there then I would have to shift all of the elements, right? You just saw it how easy it was, because since they are all like in a memory address, in a memory layout, I just had this address. After this address I put a new address, and for that new address, the next address that it is going to point to, I'm just giving it like as the next node, right? So yeah, that is it, compared to something like a vector, which in the worst case takes time complexity O of n. Cool. So this is like a very good thing in linked list, that like the insertion is very cheap, right? Now we will see what is the pain in linked list. So let's say I want to do something like insert at tail. So now for this linked list I want to insert at the tail of this linked list, right? So again I will be given a head. I'm just assuming I'll be given a head and something else. I'll just be given a value, right? Now insert at tail. Tail means the end of the linked list, right? But I don't know what the end of the linked list is. This means I would have to travel to find the end of the linked list. So what this would be something like, let's say 1, 2 and 3, and this is having null. Then I would essentially call insert at tail for this head, and like something like 4, and then this would give me 1, 2, 3, 4 and null. So yeah, this would be that. Now for this again we would have to create the node in itself, right? Now this is insert at tail, right? This means like this is going to be the last node. So what is the like property of the last node? The last node is always going to have the next element that it is pointing to as null, right? So this is something that we can use to our benefit. Now if the head is null itself, then I'm just going to create a new node and return it, right? So firstly let me just create a new node. So I'll create a new node and this will be create node with this value. If my head is null, in that case I'm just going to return this node, because if my head is null, if I don't have anything, then that is my tail itself, right? I don't have any elements at all. Then I'll just create a new node and I'll call it as my new head or like as my new tail, because we don't have anything, it doesn't matter. When the size is 0, then like head and tail, they point to the same place, right? Okay, now if that is not the case, then this means we would have something, right? So let me just create a temporary vector. I'll have this head, because what am I going to return? After this entire function, I'm again going to return the same head, right? I'm going to return the same head. It's just at the end of this, I'm going to have this new value. So this means I don't want to like operate directly with this head variable, because I will be losing that track of this, right? If I just move a bit away, then I'll lose a track of this, and then it's like I'm never going to be able to come back to that memory address, right? That's why like we'll just have a copy of this in a temporary variable. Now what else do we require? We want to check if the next element, so we want to check if the next element is equal to null. So if the next element is equal to null, then this is where we should stop. So this means we will have something like this. So while the next element of this node, like while the next node of this node is not null, we want to move ahead, right? So as long as this is not null, for example this is not null, then like go here, then this is not null, go here, then for this is null, so stop. So when we come out of this loop, we will be at the node which is going to be the last node, and for that node the next is going to be null. So what we are going to do is, for the next like pointer, the next node for temp, we are going to have this as new node, which we just created over here at the top, and that's it. Like we'll then be returning the same head, and that will be it. So this was insert at tail, this was insert after node, this was insert at head. Let me just cover one last operation that I'm thinking of. That will be something like delete a given node. So I can't delete a node directly. You know why? Because if I try to delete a node directly, I would need to have the node that it was pointing to before, right? So I can't do that. So what I would have to do is, for these things, like we would use a doubly linked list where there is a previous pointer as well. But for this one, I'll just show you in a different way. I'll still do this and I'll show you how painful this is. So let's say I want to delete a node by value, and I will give it the head. So like for linked list, always we are going to get the head, and then I'll be getting a value. So wherever am I going to find this value, basically I want to delete that node, right? So let's say I had something like 1 2 3 4, and this was null, and then I called delete node by value something like 3. Again, like we can have multiple like such like we can have duplicates, of course. So like it's just the type of logic that we implement over here. We can just remove the first value, we can remove all such values. So like those are just some custom logic that we would have to do. For this, I'm just assuming we are having duplicate, like we're not having duplicate elements, and we're just going to remove like the first value that we are going to encounter, because in most like internal implementation, it's usually that. Okay. So delete node by value 3. After this, I should be getting something like 1 2 4 and then null. Cool. So what are the things that we would be requiring? Firstly, let's check one thing. If my head is null, then I can't do anything, right? I would just return head. So this is like a very normal check that we normally do, but this is normally not going to be the case. But yeah, just a type safety. If my head is null, then I'll just return the head, like there is nothing to be deleted. Okay. Now there can be a case where the head node is the one that is having that same value, right? So if head is not null, because if it was null we would have returned from here. So if the data that is, if the so what was that, this was value, right? Yeah. So if the value that head was holding, if that was equal to this value, then this means we are in for a bit of trouble, right? Because this is the starting node and I want to delete this itself. This means like I want to remove this. And in linked list, deleting doesn't only means like just get rid of that structure. We would also want to like free that entire memory address, because in C, when you allocate memory, you would have to free it. Otherwise, you just leak memory, right? So what we are going to do is we are going to create a temporary node, and over here we are going to have the, so okay, so we are going to create a temporary node and we are just going to like reference this as my head. And now what we are going to do is I'm going to go to head, take its next. So this is the next element. So let's say I wanted to delete 1. This means that okay, this is the node, I want to get to 2. So this was the next. So I would have something like this. I mean, see, I can just directly do something like this is the next element of head, and like we would want that. So then that would be something else. But what we should rather do is, because we would have to also free the memory, we should probably have this here, and then like also store the new head. This will be heads next, and then we should free. So we should free temp. So this was the node that was like, this was the same memory address which was holding by head, and then our head will be our new head, something like this, and then we would be returning our head. Okay, so what did we do? We just like copied over this temp, and then we created a new head which will be the next element of that. And like we don't know, that can also be something like null, but if that was null then it's fine, like we would just be returning null, nothing else. Okay, and then like we assign the head to be this, and we just return this same head. Okay, now if that was not the case, if this was not the case, then let's say I would be like having this somewhere here. So I'll be having this. Now see, let's say I want to delete the node by value 3. So if I get to this point, I can no longer delete this. Do you understand? Because I don't have any track of the previous element from where I came from. This means when I'm here, then only I would have to check if the next element is equals to the one that I'm trying to remove. Okay, so what I will do is while current's next is not equal to null, that is, this is not null, and current's next node's value, this is not equal to the value that I'm looking for, right? This means there is a next node for current and it is not equal to the node that I'm looking for. Then we can just move, right? This will be just this. So like we can just keep iterating, and there will be a point where the next node will be the one that I want to delete. So this is where I'll stop. So when we get to that phase, what we will do is for that node, basically, like we will be at 2, and then we know we want to delete 3. So let's just have something, let's just have this very descriptive. So the node that we want to delete is going to be the next of current, right? So the node that we want to delete is going to be the next of current. Now there will be a node just after this node. So there will be a node just after delete, and that will be the next of this, right? So that, like, the node that I want to delete, again, the node that I want to delete, it can be the last node. So let's see how it will be for that. So for example, we have 3, so the next node is going to be 4, and the node just after this, it is going to be null. So after 3, I am going to assign it to the next node of whatever we had next. Okay, so in to delete we are getting this, then after delete, like, this is the element that we are going to get. And now for the current node, what I'm going to do is, for the current nodes next, I'm going to have this as after delete. Okay, and that's it. Like, we can just return the head and it will be done. So did you see like how painful it was? Because we had to like do a checking one step forward, where I was checking, okay, if the next element exists and if the value is not equal to this, only then like we would have to do this. So this is like a issue with single linked list, right? So these are something that double linked list is going to solve. We'll see that in our next video. Similarly, over here we saw that when we want to insert at tail, we can't just directly do a pushback like a vector, right? We would have to traverse, because for a linked list we only like keep track of the head. We can keep track of the tail as well, but like either way you would have to like do the traversion. You can't find a random node in there, right? So for that, the traversal is there. So this means in a linked list, insertion is cheap but traversal is very expensive. Okay, now let me just create a few functions. One will be print ll. So this is going to get this node, and let me just copy this somewhere. So while this is not equal to null, I'll be printing node is this, and over here we are going to have this value, and then we are going to go to the next one. Okay, similarly there will be one for freeing the linked list. So freeing the linked list, again I'll be getting this head, and over here what I'm going to have is, I'm going to copy this, and now while this temp, this is not equal to null, while this is not equal to null, what I want to do is, I want to get like the next element. So what I can do is, I can do this, and over here I can have this, right? So while my head is not equal to null, I can have the next pointer to head in tail, in temp, and I can basically free my temp, right? And then my head, I will be assigning it to temp, and that's it. Like, we'll be doing this, and like, essentially we'll be clearing out the entire linked list. Okay, so like this was it. Now let's just see a quick demonstration. Let me create a few nodes. Okay, so let's see. I'll create a head. By default I'll be making this as null, then I'll be getting this head, and I'll be passing insert at head. So over here I'll be getting this head, then I'll be giving 1, and then I'll be again doing something like head will be insert at head, and this will be head and 2. So this is going to be the opposite, like this is going to be 3 to 1, right? Because every time I'm inserting like at the head, and then this will be 3. So that's there, And next let's just print this, so print ll of head. So by this time what we are going to have is we are going to have 3, then 2, and then 1, and this would point to null. So we would be printing this. Then what we are going to do is we will be doing something like, let's say, insert at tail. So we'll be doing an insert at tail for the same node, right, for the same head. Okay, so again head will be insert at tail. I'll be giving this head, and then I'll be giving 4, and after this my like linked list should be something like 3, 2, 1, and then 4, and then null. I'll be like doing this print ll of head, and after this let us just like check these two functions that will be like this one function that will be delete node by value. So we'll be deleting this one node by value. So head will be delete node by value. Over here we will be giving the same head, and let's say I want to delete 1, right? So I want to delete 1, and then after this it should be something like 3, 2, and 4, and then null. And let's just print the linked list again. So print ll, and we'll be giving this head, and that's pretty much it. After this let's just free, so like we have this free ll, and over here we are going to have this, so we are going to free the memory. And let me just see if there is anything else anywhere that I am missing out. Maybe a new line over here, creating stuff over here, and let me just put one small thing, that if new node is equal to null, then like I'll just print if something like memory allocation failed, just a good practice, and like we can just exit, right? Cool. Let's see if this compiles. So this compiles fine, and now let's see the update. So 3, 2, 1, this was our initial stuff. Then we had 3, 2, 1, 4, this was again our stuff. Then we have 3, 2, 4. So did we expect this thing? Let's see. So 3, 2, 1, okay, then 3, 2, 1, 4, and then 3, 2, 4. Now malloc error object pointer being freed was not allocated was set. Okay, so this means there is some issue with this. So while this is not equal to null, okay, so let's see what is the issue. Like our code works, but in the freeing of the linked list there is a bit of a memory issue. So we get the head, we check if this is not null. If this is null, like if this is not null, then I'm getting the next element and I'm storing it over here. Okay, then I would have to do this, right? I would have to free the head, right? Not that. So I would have to free this, and then like my head would be this. Cool. I think this would be correct. Yep. So 3, 2, 1, 3, 2, 1, 4, and 3, 2, 4. So yeah, like that was it. That was all about like singly linked list, and in the next video we will see how we can do double linked list. We will be having a previous pointer, and then we will essentially see how the std list in C++, how it is implemented like under the hood. And yeah, like that's how we will be doing. I hope you have a better idea of linked list and how to implement them from scratch. So yeah, thank you for watching.